Welcome back, guys. This is 4.3, derivatives and the shapes of graphs. Okay, so on 4.1, we learned how to find critical numbers. So critical numbers were for the first derivative, and we also learned how to test them in a closed interval to find an absolute max or minimum. Well, today, we are going to find critical numbers. We're going to look for max and minimums using a sign chart. And then we're going to take the second derivative and we're going to look for points of concavity, which are called inflection points. And we will be using the sign chart for that as well. We will then combine all of that to help us graph a function based off of the characteristics of the first derivative and the second derivative. So let's get started first. We look at the increasing, decreasing test. A says if the derivative is positive on some interval, then f is increasing on that interval. So remember that derivative is just a slope. So what A is saying is that if the first derivative is positive, then the original function must be increasing on that interval. B says if the first derivative is negative, then the original function must be decreasing on that interval. Okay, so we'll get into the first derivative test next. And based on our critical numbers and our sign chart, it is possible to find maximums and minimums. So for the very first example, it says, let C be a critical number of f. Then we'll construct a sign chart for the first derivative close to and on either side of our critical number. So for number one, we have a local minimum if the derivative changes from negative to positive at our critical number. So this means that our function will decrease and then increase. So decrease and then increase. This means that, well, if I drew a better graph of it, maybe here. So if I had a little graph here, this means that if my function decreases and then increases, we have a minimum. That point would be a minimum. Okay. And then you have a maximum if your derivative is positive and goes negative. This means that if I do my graph again, let's say my function now increases and then decreases. This high point would be a maximum. So you increased and then you decreased. Okay. Then let's say if our signs don't change. Number three, we do not have a max or minimum at all if we go from increase to increase. There is no change in sign, there is no change in direction, therefore there is no maximum or minimum. And then you could say the same for the fourth one. You don't have a max or minimum if you decrease and decrease. There is no change in the function. So there it is. So in order to find our max and minimum, for minimums, first thing you must do is decrease and then increase to have a minimum. To have a maximum, you must increase and then decrease. So that's what we're going to be looking for today. Maximums and minimums, and we will do it based on a sign chart. Okay. Example one. Find where the function f of x equals 3x to the fourth minus 4x cubed minus 12x squared plus 5 is increasing and decreasing. Then find local minimum and maximum values. So to find local max and minimums, here's the process. You're going to take the first derivative. You're going to set it equal to 0 and solve for x. Whatever values you find are called critical numbers. You will take these critical numbers, plot them on a sign chart, pick test points, test those test points on the sign chart, and those test points will tell you where the derivative is positive and negative and where the original function's increasing and or decreasing. Once we make that sign chart, we will be able to find where we have maximums and where we have minimums. So we just add an extra step to what we learned on 4.1. Okay, so let's get started. So step A says find the derivative. So that's where we'll go first. All right, A, we take the derivative, behave. F prime of x is going to be 12x cubed minus 12x squared minus 24x. 12x cubed minus 12x squared minus 24x. Then we take the derivative and set it equal to 0. 12x cubed minus 12x squared minus 24x equal to 0. Solve this for x. I'll just divide everything by, oh no, I won't. I'll factor out a 12x. Why not? Take a 12x out. This should leave me with x squared minus x minus 2 equal to 0. Then factor, and you'll get 12x equals x minus 2 and x plus 1 equal to 0. X squared, 1x, negative 2, good. Then set all three equal to 0, and we'll get x equals 0, x equals 2, x equals negative 1. All of these are my critical numbers. Okay, not bad. Now, step B is create a sign chart. Let's make a sign chart. So step B, we'll put a sign chart down. This is from negative infinity to positive infinity, and I will plot my critical numbers. Negative 1, 0, 2. And now I will state my intervals. My intervals on this number line are from negative infinity to negative 1, negative 1 to 0, 0 to 2, 2 to infinity. The next thing I'm going to do is pick test numbers on this interval, on these intervals. So I will have from the first test interval, negative infinity to negative 1, I will pick negative 2. From the next test interval, negative 1 to 0, I will pick negative 0.5. Then from 0 to 2, I'm thinking of a number between 0 and 2. 1.5, perfect. Just kidding, pick 1. And then from 2 to infinity, I will pick 3. Okay, so this is a sign chart for the first derivative. So these numbers you will plug into the first derivative. So plug these numbers in to the first derivative. So I should have f prime of -2, f prime of -0.5, f prime of 1, and f prime of 3. Okay, so let me look at my first derivative, which is there. I'm going to use the calculator table trick to make this a lot faster. 12x cubed minus 12x squared minus 24x. 12x cubed minus 12x squared minus 24x. Enter. Now come back down to these numbers, and -2 gives me -96. So what that means is, well, let's look at our sign chart, is that since -2 came from this interval -infinity to -1, and the output was negative, this means that from -infinity to -1, the first derivative is negative, which means the original function is decreasing. Now let's go back to our numbers. And -0.5 gives me 15 halves. So a positive 7.5 or 15 halves. So coming back here, what this means is that from -1 to 0, the first derivative is positive, which means the original function is increasing. Let's keep going. Type in 1. I get -24. Come back up. And again, this means on 0 to 2, I got a negative output, which means the first derivative is negative, which means the original function is decreasing. Now, last number. Type in 3. I get a positive 144. So I don't really care about the numbers. I only care about the sign. So the signs that we've gotten so far are negative, positive, negative, positive. I could care less what that number is. So negative, positive, negative, positive, which means that from 2 to infinity, we were positive, which means the original function increased. Okay, there's B. Now, step C, let's look for maximums and minimums. C, let's find maximums and minimums. So put that, actually label that. Find maximums and minimums, which means we have to look at our sign chart. Let's look at -1. At -1, what is our sign chart doing? It is decreasing and then increasing. Decreasing and then increasing. This means that at -1, we have a minimum. So I'll come back down here and I'll write it here. X equals -1 is a minimum. Okay. Now let's go look at our sign chart again, and let's look at the next critical number, 0. What is my sign chart doing at 0? It is increasing and then decreasing. Increase and decrease, which means 0 is a maximum. So what we do next is we say x equals 0 is a maximum. And let's look at our last critical number of 2. What is our graph doing? It is decreasing and then increasing. Decrease, then increase means that 2 is going to be a minimum. That means 2 is a minimum. So we say x equals 2 is a minimum. Okay. So with that being said, -1 and 2 are minimums, 0 is a maximum. And since we will be graphing these type of functions later on, we want to know where is the exact location of these maximums and minimums. So what you're going to do to find the exact location is take all of these values and plug them into the original function. Because remember, we're doing first derivatives and second derivatives to get the characteristics of the original function. So we're graphing the original function. So to find the exact location of these maximum and minimums, plug these into the original function, right? So plug into f of x, which means if we do so, I'll have f of -1, f of 0, and f of 2, which means that we have to look at the original function, where I'll use our table trick again in the calculator, just to make everything faster. 3x to the 4th minus 4x cubed minus 12x squared plus 5. Come back down, zoom in, and if I type in -1, I get 0. 0, I get 5, and 2, I get -27. So I have at -1, 0. That's where 1 minimum is. 0, 5 is another maximum. And 2, -27 is my other minimum. And this is what we are looking for. That is the exact location of the maximums and minimums of the original function. Whew, huh? Crazy. But crazy easy. Just tedious, I guess. Okay. Let's do it again for another function. Okay. So we're given g of x equals 2 sine x plus x, and we only want it on the interval 0 to 2 pi. Okay. We want to find the max and minimum, so where we increase and decrease. So just like before, step 1 is find the derivative. So step 1, g prime of x gives me 2 cosine x plus 1. 2 cosine x plus 1. Then, of course, you set it equal to 0. 2 cosine x plus 1 equal to 0. Rearrange, solve for cosine. You should get cosine x equals -1/2. And now we ask ourselves, on the unit circle, where is cosine -1/2? And that's going to be at 2 pi over 3. And where else? 3 pi, so 4 pi over 3. These are my critical numbers. All right, step 2 is your number line, sign chart. And remember, the interval they gave us is a sign chart on 0 to 2 pi. That's just given in the example above. So that kind of makes our sign chart a little easier to work with, maybe when it comes to radian values, right? So here's 0, and here's 2 pi. Okay, which means that 2 pi over 3, actually I'm just going to write values on the unit circle. So 0, next is pi over 2, next is pi, and next is 3 pi over 2. And now I'll plot my actual critical numbers. So 2 pi over 3 is right here. There's 2 pi over 3. And then 4 pi over 3 is right here. 4 pi over 3. So this means that my intervals are going to be from 0 to 2 pi over 3, 2 pi over 3 to 4 pi over 3, and then 4 pi over 3 to 2 pi. The reason I put the other parts of the unit circle is so I could plot the exact location of where 2 pi over 3 and 4 pi over 3 are. Okay, which can honestly help us pick critical numbers. I mean, test points, sorry, test points. So next is test numbers. And we get from 0 to 2 pi over 3. Look what value is right before 2 pi over 3. See, this came in handy. Pi over 2. We'll do x equals pi over 2. And then from 2 pi over 3 to 4 pi over 3, look what other value came in handy. That little pi there. So we'll choose x equals pi. And then from 4 pi over 3 to 2 pi, again, that other value that comes in handy is 3 pi over 2. And remember, plug into f prime of x. So I'll have f prime of pi over 2, f prime of pi, and f prime of 3 pi over 2. Use my calculator trick and make sure you are in radians, okay? Make sure you're in radians. So I'll look at my first derivative. 2 cosine x plus 1. And then I'll type in these values. Okay. So if I type in pi over 2, please don't be 0. Perfect. You get 1. If I type in pi, I get negative 1. 3 pi, let's see, 3 pi over 2, I get 1. Okay. Now I'm going to erase these so they're out of the way. Oops. Nope. There we go. Okay. So again, I don't care about the number. I only care about the sign. So from 0 to 2 pi over 3, we got a positive output of positive 1. We got a positive number. So this means from 0 to 2 pi over 3, we are positive and increasing. And then the next number was negative 1. So back to my sign chart, was negative 1. This means that from 2 pi over 3 to 4 pi over 3, we are negative and decreasing. And then the last number was positive 1, which means we are positive and increasing. There we go. Okay. And then step 3 is look for maxes and minimums. Max and mins. So which means we look back at our sign chart and we're going to look at 2 pi over 3. What does my sign chart do at pi over 3? 2 pi over 3. We increase and then we decrease, which means 2 pi over 3 is a maximum, right? 2 pi over 3 is a maximum. So x equals 2 pi over 3 is a max. And then we look at the next critical number of 4 pi over 3. What does my sign chart do at 4 pi over 3? It decreases and then it increases, which means 4 pi over 3 is a minimum. X equals 4 pi over 3 is a minimum. Okay. Well, if we want to find the exact location, take these values and plug into f of x, right? Plug into f of x. Which means that we'll have f of 2 pi over 3 and f of 4 pi over 3. I'm going to come back and look at my original function. Well, here was g of x, but you get it. Okay, which is 2 sine x plus x, 2 sine x plus x. And I'll go down, I'll type my numbers in, parentheses 2 pi over 3. I get 3.82, 3.83, 3.83. And then parentheses 4 pi over 3, I get 2.46. Which means that 2 pi over 3 and 3.83 is my max, right? That's my max. And 4 pi over 3 and 2.46 is my mid. There it is. Not bad. Okay, especially with trig functions, right? Yay, fun. All right. Example 3. Do it again. Find where this function increases and decreases, then find max and min values. Okay, so right now you're just along for the ride, right? So we're on step 1. F of x equals x over x squared plus 1. So that's f, that's g, which means f is x. G is x squared plus 1. F prime is 1. G prime is 2x. This means that f prime of x is f prime g. X squared plus 1 minus g prime f, 2x squared over x squared plus 1 squared, which means f prime of x is negative x squared plus 1 over x squared plus 1 squared. All right, there's the derivative. Now we set it equal to 0. And negative x squared plus 1 over x squared plus 1 squared equal to 0. Remember this one, you'll have a piece from the numerator. Since it's rational, we'll get a piece from the numerator, which means I get negative x squared plus 1 equal to 0. Negative x squared equals 1, x squared equals 1. And from the numerator, we get critical numbers of x equals plus or minus 1. All right. From the denominator, we get x squared plus 1 equal to 0. And you would get x squared equals negative 1, but there are no critical numbers from this one because this is imaginary. So these are my only critical numbers. Okay. All right. Well, I almost took up the whole page, but we still got room. So I'll just do step 2 over here with the sign chart. So step 2, sign chart. There's negative infinity, there's infinity. The only numbers we found were negative 1 and 1. Which means my intervals are negative infinity to negative 1, negative 1 to 1, 1 to infinity. My test numbers are going to be from negative infinity to 1, I'll pick negative 2. From negative 1 to 1, I'll pick 0. And from 1 to infinity, I'll pick 2. Remember, we're plugging these numbers into. Plug into f prime. So f prime of negative 2, f prime of 0, f prime of 2. Let me go look at my derivative. Where are you at? Right there. I'm going to type that in my calculator, use my table feature. negative x squared plus 1 over x squared plus 1 squared. Enter, enter, enter. And I'll show you how much I care about numbers. When I type in -2, I get a negative output. Don't care, it's negative. I type in 0, I get a positive output. I type in 2, I get a negative output. See, told you, the number outputs don't matter, just the sign. So from negative, we're negative, positive, negative. So this means that we are negative and decreasing, positive and increasing, negative and decreasing. Negative, positive, negative, just like the signs we got from our test numbers. And now, step 3, we look for max and min. So I'll do that down here. 3, max and mins. All right, let's look at our sign chart when we have 2 numbers. So, let's do this real quick. -1, decrease, increase. -1 is a minimum. +1, increase, decrease. +1 is a maximum. So -1 is min, +1 is max. So x equals -1 is my min, x equals +1 is my max. Now plug these into f of x, right? Plug into f of x, because you're trying to graph the original function. And this become f of -1 and f of 1. This gives us the exact location of those max and mins. And what's my original function? X over x squared plus 1. So type that in my calculator. X over x squared plus 1. And scrolling down. If I type in -1, I get -1/2. If I type in 1, I get +1/2. So this point, -1, -1/2, that is my min. And then this point, 1 and 1/2, that is my max. The exact location of these maximum and minimums. Okay. Perfect. Looking good. Hopefully no mistakes. That was terrible math. You're welcome. Okay, moving on. All right. So now we look for concavity. And to find concavity, we need the second derivative. So below are just examples of what concave up and what concave down look like. So first picture is concave up. So concave up can look like that, or concave up can even look like this, right? These are examples of concave up. Concave down is the second picture. Concave down can look like that, or concave down can look like that. So we will be looking for concavity. All right. Now the other definition is inflection points. And an inflection point comes from the second derivative. But in order to be an actual inflection point, concavity must change. You must go from concave down to concave up, or you must go from concave up to concave down. as shown in the examples here. So with these examples, B would be an inflection point because it goes concave down to concave up. So all of this part is concave down, and then all of this part is concave up. Okay. And then C would be an inflection point because it goes concave up to concave down. So C would be an inflection point. And then D would be an inflection point because we were going down and now we're going up. So D would be an inflection point. And then for E, since we're going concave up and this is also concave up, E is not an inflection point because concavity did not change. Remember, to be an inflection point, concavity must change. And then you get to P, it goes concave up to concave down. That is an inflection point. Okay. So next is the concavity test. If the second derivative is positive on some interval, then the original function is concave up. If the second derivative is negative on some interval, then the original function is concave down. So that's all we're saying. So for the first definition, if you're positive, if your second derivative is positive, you're concave up. If your second derivative is negative, you're concave down. Okay. Or maybe you're even concave up, and then you go to concave down, or the other way around. So, something to think about when it comes to concavity. All right. The next piece, use it if you want, or don't use it at all. It's called the second derivative test, and the only reason it was created is to skip the sign chart for the first derivative, which means by the second derivative test, you would take your critical numbers from the first derivative and plug them into the second derivative. And if the outcome was that the second derivative was negative at your critical point, oh, I'm reading them backwards. Oh well, number 2. If the second derivative is negative at your critical number, then you have a maximum because your graph would look like this. And that high point would be a maximum. What the first rule says, now that we're going in order, it says if the second derivative is positive at this critical number, then you'll have a local minimum, which means that our graph would look something like this. And the low point would be the local minimum. And then here comes number 3. If your second derivative at the critical number is 0, then it fails and you need to create a sign chart for the first derivative. This is why I say don't use it at all, because we're getting into the second derivatives now. So no matter what, you have to take the second derivative. So it could make your life easy, but it fails. If it fails, then you're back to everything the long way. So, I mean, I can definitely show you how it works if I remember to at the end of this problem. I'm gonna work everything out like normal, and then we'll go to the second derivative test at the very end. I'll show you. Okay, so 4, given x to the 4th minus 4x cubed, find concavity, point of inflection, max and mins, and use all this information to sketch the curve, okay? Use all this information to sketch the curve. So, step A is purely algebraic. You find the domain, and you find the x and y intercepts. Cool, easy, let's do that. So, step A, find the domain in x-intercepts. So that's what we'll do. We are given f of x equals x to the fourth minus 4x cubed. X to the fourth minus 4x cubed. Just making sure I wrote that down correctly. Good. So this is a polynomial function, which means our life is good because guess what the domain of all polynomial functions is? Negative infinity to infinity. But now it says to get x and y intercepts. So we go back to 1414, maybe even 0320. Welcome back to 0320, guys. We're finding an x-intercept, which means if you find an x-intercept, you let y, or f of x, equal 0, which means you take x to the fourth minus 4x cubed, set it equal to 0, and solve for x. So this is step A. So I can take out an x cubed, which would leave me with x minus 4 equal to 0, which means it's completely factored, which means I would get an x-intercept at 0, and I would get an x-intercept at 4, which means convert these to actual x-intercepts, and I get the points 0, 0, 4, 0. These are my x-intercepts. Now, I want my y-intercept. To find a y-intercept, you let x equals 0. So this means we'll have f of 0, but if I plug in 0 to x to the fourth minus 4x cubed, I'm just getting 0. So this means that 0, 0 is my y-intercept. Step A is done. Domain, x-intercept, y-intercept. Here it's too not colorful, so there you go, to separate them. Okay. B, find the max and minimums. Ooh. So that means everything we learned so far. Take the derivative, find critical numbers, plot them on a sign chart, test, find max and mins. So we know how to do that, okay? So here comes B. B, find max and mins. So that means we're going to take the derivative, which is 4x cubed minus 12x squared, right? X to the fourth, 4x cubed, negative 4x cubed, negative 12x squared. Okay. Take that derivative, set it equal to 0. 4x cubed minus 12x squared equal to 0. Factor out a 4x squared, that leaves me with x minus 3 equal to 0. Set those equal to 0, and I'll get x equals 0 and x equals 3. These are my critical numbers, right? And then for step B, we make a sign chart. So I'll put that over here. Sign chart. Here's negative infinity, here's infinity. Plot my critical numbers, which were 0 and 3. 0 and 3. Now you see my intervals of negative infinity to 0, 0 to 3, 3 to infinity. Pick my test numbers. I'll get x equals negative 1, x equals 1, and x equals 4. Remember where to plug those numbers in? into the first derivative. So I'll have f prime of -1, f prime of 1, f prime of 4. Now let's go to my derivative. Use my table trick for the function, for the test numbers, 4x cubed minus 12x squared. And remember, I really don't care about the number. I only care about the sign. So -1 gives me -16. 1 gives me -8. 4 gives me 64. Hey, look at that. We got a negative, right? Okay. Or again, since I'll use my calculator, that's negative, and positive. Since I said numbers don't care. Okay. Now when making the sign chart, from -infinity to 0, since we picked -1, I got negative, which means we decrease. 0 to 3, I got again negative, which means we decrease. 3 to infinity, we got positive, so we increase. All right, we're looking for max and mins, so let's look at our sign chart. And let's look at 0. 0, we decrease, which means nothing happens. So x equals 0 is nothing or neither. And then let's look at 3. 3, we decrease and increase, which means x equals 3 is a min. Which means since we're actually going to graph this, yes, let's find the exact location of that minimum. So we only care about the min, which means that this becomes f of 3, which will give me, where's my original function? I got x to the 4th minus 4x cubed. And I'm just typing in 3. Three gives me -27. -27. So our minimum is at 3, -27. This is my min. All right, guess what? That was everything we learned today. Now we go into something new. We're going to look for inflection points, okay? We will look for inflection points. Okay, so that means we're going to take the second derivative. Okay, we're going to do the second derivative. All right, should do it in green, sure. So let me get the second derivative down. So C, we're going to look for inflection points. So this means we're going to do f double prime of x. So we're doing the second derivative, which above would be 12x squared minus 24x. Perfect. Okay. Then take your second derivative. Zoom in. Take your second derivative, set it equal to 0. You get 12x squared minus 24x equal to 0. Solve for x. Take a 12x out, and you're left with x minus 2 equal to 0. Set these ones equal to 0, and you'll have x equals 0 and x equals 2. These now are called my inflection points. And they are possible inflection points because we have no idea if the concavity is going to change at these points until we make a, guess what? Sign chart. We have to make a sign chart. Plot these inflection points. I can fit it here. Where's my graph? Down there? Tons of room. So let's make our sign chart. There's negative infinity, there's infinity. Plot my inflection points, 0 and 2. And again, there's my intervals. Negative infinity to 0, 0 to 2, 2 to infinity. Pick your test numbers. From negative infinity to 0, we pick negative 1. From 0 to 2, we pick 1. From 2 to infinity, we pick 3. Now, there's something different here. This is a sign chart for the second derivative. So these numbers you plug into f double prime of x, because this is a sign chart for the second derivative. So f double prime of negative 1, f double prime of 1, f double prime of 3. And again, just like the other ones, I only care about the sign. So where's my second derivative? Go ahead, use the table feature, 12x squared minus 24x, 12x squared minus 24x. Come down, plot these numbers, negative 1, I get a positive output. 1, negative, 3, positive. So we're positive, negative, positive, which means come look at our sign chart. From negative infinity to 0, we are positive, increasing. And now, since this is a sign chart for the second derivative, we will be concave up. From 0 to 2, we are negative, which means we are decreasing, which means we will be concave down. Then, from 2 to infinity, we are positive, which means we are increasing, which means we are concave up. Okay. Which means that now, look at our numbers. We're going to first look at 0. We want to know, is 0 an actual inflection point? Did concavity change at 0? And the answer is yes. At 0, we went concave up to concave down. Concave up to concave down. This means that x equals 0 is an inflection point. And then let's look at 2. Did concavity change at 2? We went concave down to concave up, which means did concavity change? Yes, which means x equals 2 is also an inflection point. Oh, but we're not done, because Now, since they are inflection points, we need to find the exact location of inflection. We need to find the point of inflection. So guess what that means? You take these numbers and plug into f of x, the original function, because that's what we are graphing. So these will become f of 0 and f of 2. Now, what was my original function? There you are. Plug you in my table. X to the 4th minus 4x cubed. X to the 4th minus 4x cubed. Okay. And then what we're going to plug in is 0 and 2. Well, 0 is easy. 0 gives me 0. So 0, 0. 2, I get negative 16. These are my actual points of inflection. And now we're ready to graph. Starting with step 1. Step 1 says, plot your x-intercepts. My x-intercepts are at 0, 0, and 4, 0. And my y-intercept is also at 0, 0. So all we have to plot are 2 points, 0, 0, 4, 0. Let's go. Zero, 0. A little off, too big. 0, 0, 4, 0. Everything from step 1 is done. Okay. And then, step B, plot your minimum. The only point we plot from this one is 3, negative 27. 3 and negative 27. So I'm just going to put that point somewhere here. 3, negative 27. There's my minimum. I'll even write it there. All right. Not accurate, but hey, it's a sketch, right? Okay. Everything we need from step B is done. Now, step C. Plot the only 2 points we found. Points of inflection. 0, 0, 2, negative 16. Well, look at that. 0, 0 is already plotted. Now we need to plot 2, negative 16. Well, if I put 3, negative 27 down there, then 2, negative 16 is going to be somewhere around here. And I'll label it for you as well. Two, negative 16, that's my point of inflection. Oops. 0, 0, that's my other point of inflection. It's also my X-intercept and my Y-intercept. Okay. Now you're wondering, how do we finish this graph off? We finish this graph by using the sign chart for concavity above. We use this lovely sign chart. So our sign chart says that from negative infinity to 0, we are concave up, which means come down to my graph. So from negative infinity to 0, so from negative infinity to 0, we are concave. Oops. Concave up. This is concave up. All right, look at the sign chart again. From 0 to 2, we are concave down. So here is 2, right? There's 0, there's 2, there's infinity, there's negative infinity. So what we're saying is that from 0 to 2, we are concave down. So we change direction. We go concave. No, stop it. Concave down. This part here is concave down. Look at the sign chart one more time. Because from 2 to infinity, we are now concave up. 2 to infinity, we are now concave up. And looking at our graph, from 2 to infinity, we now change direction at this point of inflection and we go concave up. And all of this is concave up. Whew. That is just a taste of what we're going to get in 4.4 or 5, whatever it is, curve sketching. Oh, okay. Okay. Oh yeah, I said I would show the second derivative test, show you how it works. So this means that I'll show you really quick. I won't write it down. Well, I won't save it, but you'll see it on the video. So if we do the second derivative test, I take my critical numbers from step B and I plug them into the second derivative. So this means my critical numbers from above were 0 and 3, which means I would have f double prime of 0 and f double prime of 3. Well, what we're looking for is positive or negative outputs. So if I plug in 0 to the second derivative, we get 0, which means fail, which means you still have to create a sign chart. So it's not even worth going on. But if I plug in 3, I get 12 times 3 squared minus 24 times 3. I get a positive output, which means that if the second derivative at our critical number of 3 is positive, this means that x equals 3 is a minimum, which, hey, That's proven right there. But since this failed, you still have to create a sign chart just to make sure it's not a max or min. And that's how the second derivative test works. You would skip a sign chart, but if it fails, you still have to make a sign chart. Use it if you want. I don't. And the reason I don't is because, well, it's just an extra step. You're going to have to find the second derivative anyways, so just keep going. Okay, there it is. Beautiful. Last one. Ooh, how long did that one take? That one took like 30, 40 minutes, I think. I don't know. Who knows? Okay, so we're gonna do the same thing on this one. Concavity, maxes, mins, all the good stuff. Follow the steps. I'm just gonna go on this one. So here we go. A. First off, I see a mistake. It says f of x equals 2 cosine theta. Since it's all in terms of theta, this x needs to be a theta. That's it. My bad. Okay. So take the derivative. Actually, before we take the derivative, I need to rewrite something. I have f of theta equals 2 cosine theta plus cosine theta squared. And now I take the derivative. F prime theta is negative 2 sine theta plus 2 cosine theta times negative sine theta. And then f prime theta is negative 2 sine theta minus 2 cosine theta sine theta. Clean it up. F prime theta is negative 2 sine theta times 1 plus cosine theta. All right. Now, set this equal to 0 and negative 2 sine theta times 1 plus cosine theta equal to 0. And if I set both terms equal to 0, I'll get sine theta equals 0 and cosine theta equals negative 1. All right. We are given a restriction here from 0 to 2 pi, so we only want values on the unit circle. So for theta to be 0 on the unit circle, theta has to be 0, pi, 2 pi. For cosine to be negative 1, theta has to be just pi. These are my critical numbers. Okay, sign chart time. Actually, we're given restrictions from 0 to 2 pi. Okay, let me plot my critical numbers, and it happens that 0 is a critical number, and then pi is a critical number. Actually, it's right in the middle, right? pi is a critical number and 2 pi is a critical number. Wow, that's nice. Which means that if I wanted to put some other parts of the unit circle on here, this would be pi over 2, and this would be 3 pi over 2. So it just gives us what values to pick, which means that here my interval is from 0 to pi and pi to 2 pi. I just realized I skipped X-Intercept Y-Intercept. I'll get there in a second. I can do that last, whatever. All right. Test numbers from 0 to pi. I see it right there. X equals pi over 2. And then from pi to 2 pi, x equals 3 pi over 2. X equals 3 pi over 2. Okay, cool. Plug these into the first derivative. Okay, so what was my first derivative? Make sure you are in radians. Okay, my first derivative was right there. Table, -2 sine x times 1 plus cosine x. At pi over 2, we get a negative value. At 3 pi over 2, I get a positive value. So once again, I'm going to get rid of these markers just because I put them there just so we can see how to space out our unit circle, our number line. Okay, so based on my values, we are negative from 0 to pi, which means we are decreasing. We are positive from pi to 2 pi, which means we are increasing. This means that since we decrease and increase at pi, x equals pi is a minimum. And to find the exact location of that minimum, well, plug it into the original function, f of pi. So for that one, I have 2 cosine x plus cosine x squared. Enter and just type in pi. We get -1. So this equals -1, which means pi -1 is my minimum. Okay. X-intercepts, Y-intercepts really fast since I skipped it. My bad. B, first of all, the domain of our trig functions, cosine, is all real numbers. Even if it's cosine squared, it's still all real numbers. Okay. Then for x-intercept, we let f of theta equal 0. So what's my original function? 2 cosine plus cosine squared theta. Right, 2 cosine theta plus cosine squared. So that means I have 2 cosine theta plus cosine squared theta equal to 0. I will factor out a cosine. So cosine theta, that leaves me with 2 plus cosine theta equal to 0. Set these equal to 0. Cosine theta equals 0. Cosine theta equals -2. And for the first one on the unit circle, cosine is 0 at pi over 2 and 3 pi over 2. And for cosine theta equal to -2 on the unit circle, that is nowhere. So this one does not work, which means that my x-intercepts are at pi over 2, 0, and 3 pi over 2, and 0. Those are my x-intercepts. And then for the y-intercept, we let x equals 0, but it's not x, it's theta equal to 0, which means I'd have f of 0 equal to 2 cosine of 0 plus cosine squared 0, right? 2 cosine theta plus cosine squared theta. This would become 2 times 1 plus 1 squared, which would give me 2 plus 1, which is 3. So my y-intercept would be at 0, 3. Here's my y-intercept. Okay, that part's done. Now to the hard part. Maybe the hard part, who knows? C. Second derivative time. So I'm just gonna rewrite the first derivative, which is, okay, so there's something I'm gonna do here, and this is to make the second derivative a lot easier, okay? If I choose this form, which there's nothing wrong with it, if I choose this form, I use product rule. Nothing wrong with that. If I choose this form, I avoid product rule. And you're probably asking, how do I do that? And the answer is identities. So for second derivative purposes, this will become -2 sine theta minus, and if you remember, 2 cosine theta sine theta, that becomes the double angle formula of sine 2 theta. Now this looks a lot easier to take the derivative of. So that's what I'm gonna put right here. So -2 sine theta minus sine 2 theta. -2 sine theta minus sine 2 theta. Okay, now I'm ready. I'm going to take the derivative, and this only involves chain rule now. So my second derivative is going to be -2 cosine theta minus cosine 2 theta times 2, the derivative of the inside, which means that this becomes f double prime theta equal to negative 2 cosine theta minus 2 cosine 2 theta. Okay, we have to clean this up more. I have to bring in more identities because I can't leave cosine 2 theta like this. So cosine 2 theta has 3 identities. We're only going to choose the one that involves just cosine squared, which means cosine 2 theta is the same as 2 cosine squared theta minus 1. 2 cosine squared theta minus 1. Okay. Okay, and then since we're changing it to that, this becomes f double prime theta equal to negative 2 cosine theta minus 2 times 2 cosine squared theta minus 1. Let me just double check that double angle formula. Cosine 2x, 2 theta, 2 cosine theta minus 1. Yep, we're good. Okay, so this means we get f double prime theta equal to negative 2 cosine theta minus 4 cosine squared theta plus 2. All right. Rearrange this one more time. F double prime theta equals, I could take a negative 2 out if I want, so why not? Negative 2 times 2 cosine squared theta plus cosine theta minus 1. That'd be negative 4 cosine squared, negative 2 cosine squared, plus 2. Okay. Ooh, there's a second derivative. Now we set it equal to 0. And I don't need that negative 2 anymore, so I'm just going to leave that off. I set 2 cosine squared theta plus cosine theta minus 1 equal to 0. I can factor this as 2 cosine theta minus 1 and cosine theta plus 1 equal to 0. That's 2 cosine squared, 2 cosine minus cosine. Good. Set these equal to 0. And I get cosine theta equals 1/2. Cosine theta equals negative 1. And now, ask ourselves, where on the unit circle is cosine equal to 1/2? Where in the unit circle is cosine equal to 1/2? That will be pi over 3, and then 2 pi over 3, 4 pi over 3, and 5 pi over 3. And then where is cosine equal to negative 1? That's at pi. These are my inflection points. These are my possible inflection points, my pips. Now we do a number line. Is there any more room? Of course, tons of it. So here's this, here's that. Actually, we're given a unit circle again, right? Lucky us. There's 0, there's 2 pi, and then we know that pi, which is my inflection, one of my possible inflection points, goes right in the middle. Again, I'm going to put the unit circle down so I know where to place pi over 3 and 5 pi over 3. Here's pi over 2. And here is 3 pi over 2. This means that my inflection point of pi over 3 should be right here. And my inflection point of 5 pi over 3 should be right here. Now I'll get rid of them. There you go. And now you see your intervals. 0 to pi over 3. Pi over 3 to pi. Pi to 5 pi over 3. And 5 pi over 3 to 2 pi. Pick your x values. From 0 to pi over 3, what fits in there? Pi over 4 does. From pi over 3 to pi, we can do pi over 2. From pi to 5 pi over 3, we can do 3 pi over 2. And then from 5 pi over 3 to 2 pi, I think we can do 5 pi over 3 is there. So you could do 7 pi over 4. And remember, you're plugging these into the second derivative. Which means, let's look at our second derivative, which is right where we're at. One of these will work. Make sure you include the -2 on there. So if I plug this into my second derivative, -2 cosine x minus 4 cosine x squared. Minus 4 cosine x squared plus 2. Enter, 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 enter. And if I'm plugging these in, let's see. Pi over 4 gives me something negative. Pi over 2 gives me positive. 3 pi over 2 gives me positive. And 7 pi over 4 gives me negative. All right, kids, we're ready. Look at this sign chart. We're in minus, plus, plus, minus. So from 0 to pi over 3, we are negative, which means we're decreasing, which means we're concave down. From pi over 3 to pi, we are positive, which increases, which means we're concave up. And then again, positive, and concave up, and then negative, which means we are concave down. Oh man, which means almost there. Look at our sign chart. And this means look at pi over 3. We go concave down to concave up. So this means pi over 3 is an inflection point. So down here, x equals pi over 3 is IP. Come back up. Look at pi. We go concave up to concave up. Concavity does not change, so we do not care about pi. And then look at 5 pi over 3, concave up to concave down. Concavity changes. So x equals 5 pi over 3 is IP, which means we're almost done. Take these and plug them into the original function. I'll use my calculator. 2 cosine x plus cosine x squared come back down, and if I type in pi over 3, I get 5/4 or 1.25. So pi over 3 and 1.25. Then if I type in 5 pi over 3, you also get 5/4. 5 pi over 3 and 1.25. These are my points of inflection. Oh boy. Which means we are ready to graph. Oh, oh, yeah. Okay. So we'll start with, oh, you can plot the points in any order. So from step A, I got a minimum at pi and -1. Pi and -1. So I'm going to make this chart accordingly as the unit circle. So this is going to be 0, pi over 2, pi, 3 pi over 2, and pi. And then 1, 2, 3. And then -1, -2, -3. Okay, so we said the very first point we found was pi -1. That's our minimum. Let's add a cool color here. Galaxy, rainbow, sure, look at that, rainbow. Okay, pi -1. There's the first point. That is our minimum. And then, what were my X-intercepts and Y-intercepts? That what we did second. My X-intercepts are at pi over 2 and 3 pi over 2. Pi over 2, 3 pi over 2. And I think my Y-intercept I saw was at 3. There you go. It was like infinity stones. Watch Avengers. You have the time. All right, so we have plotted the minimum. We've plotted the X-intercepts and the Y-intercept. Now all we have to do is plot my points of inflection, which were right there. Pi over 3 and 1.25. So let's put pi over 3, let's say like right around here. Pi over 3, and then let's put 5 pi over 3 right around there. Both of them have y values at 1.25. So like right here and right there. Now all we have to do is graph by concavity. So look at our concavity chart. From 0 to pi over 3, we are concave down. So if I go here, this is concave. Whoops. This is concave down. And then from pi over 3 to pi, we go concave up. That's concave up. And then from pi to 5 pi over 3, we're concave up again. So we curve up. And then from 5 pi over 3 to 2 pi, we are concave down. So we curve that way. And I realize that says just pi. That should be 2 pi. So right there was my minimum. I guess I can make that a point that's visible, right? There was my minimum. And then at 5 pi over 3, there was my point of inflection. And then at pi over 3, and right there, that was my second point of inflection. And then here was my X-intercepts, one there, Y-intercept there. Voila. Oh yeah, concavity. All of this, starting here, is concave up. And then this part, concave down. There you go, children. Man, I don't know how long that took, but that was great. Okay, just a good old time. I guess I should put points here too for you. 0, 0 was 1. 216 I put there. X-intercept also there. And then 327 was our minimum. All right, guys, that was it. That will lead us into actual curve sketching, which is going to be a lot more information, but we are done. See y'all later.